This video is going to be very much an overview of key statistics vocabulary. Statistics is its own language. We tend to think of computer programming as an analogy to a language, but you can kind of think of statistics as an analogy to a language as well. So let's break down some of the key terms that we're going to be using left and right as data scientists. So the first word is a population. When we are doing statistics, we are really interested in a population. That is the universe of cases we want to describe. This could be a population of people, of course, but it doesn't have to be. We could say, for example, how will the United States, or how will every voter in the United States vote in a particular election? We could say, what is the average income in Britain by household or by person? Here is an example of a very impoverished family in Britain. We care about the population, generally speaking. What is the population of all Americans think? What does the population of all Europeans think? What does the population of all dogs in Manhattan think, hypothetically? And the thing that we care about them, so their vote intention, their income, if they're dogs, their ability to retrieve, we call that the population parameter. Population parameter. Outside of a census, and even frankly with a census, we usually cannot study the population directly. So a sample is a subset of the population. So we're almost always working with samples, and we're going to use those samples to estimate parameters of the population. So I want to know what the effect of a drug is on people everywhere in the world. I'm going to take a random sample of 100 people, evaluate it with them, and then extrapolate back to the population. Because I cannot study the full population, we're going to talk, as we do statistics, about the uncertainty of the estimates that we make about our sample as we project them back to the population. This is like both a basic and very deep point. And it took me a while as a person learning statistics. I've said this before to my students, learning statistics in particular, separate from coding and all the other research design, something for me at least about learning statistics took exactly 3 full exposures to like really get it. So I took a statistics class in college and I was like, I'm hanging in there. I took it again in grad school and I was like, okay, that makes a lot more sense. Like I sort of memorized it in college, and in grad school, I got a better understanding of like, oh, this is why this is the case. And it really wasn't until I taught it and like really went through all the textbooks again. I was like, oh, I see. Part of it is that teaching is a great way to learn anything. But generally speaking, statistics is like, it goes from very intuitive and trivial to impossible very quickly. But at the end of the day, what we're doing is we're saying, hey, I've got a sample. I want to understand how this sample relates to the world and how confident I can be in any inferences I make about this sample in applying it to the whole wide world. That's like what we're doing a lot of the time. All right. So generally, when we're doing data science, we're doing statistics, we're doing any kind of research, ideally we have large random samples. If we do not have large random samples, we run into some problems. We'll talk more about those to come. So randomness. Why do we care about random samples? Well, what we mean is that units are chosen in a non-deterministic way by chance to participate in the study. I'm not saying, hey, anyone who stops at my booth and tells me what they think of the president is in my sample. I'm saying I am going to, do a random digit dial of phone numbers, or I'm going to pick people based on some trait that has nothing to do with their approval levels of the president in order to participate in my study. So ideally, not always possible, ideally we have random samples. The ideal setup for research to study the effect of one thing on another is randomized controlled trial. We randomly assign people to treatment and control, and we do so because we don't want someone to select into treatment or control. We imagine that someone might, again, if it's a drug trial, the people who sign up for a research study already are probably maybe more sick or more open to risks or whatever it is that's driving them to join the study. We can't randomly bring people into a study. I almost said unfortunately, but it's good for ethical purposes that we can't randomly drag people into research studies, medical studies. But once we have our 100 people, say for our drug trial, we randomly assign 50 to treatment and 50 to control. Because if we said, hey, 100 people, which 50 of you want to be in the treatment? Probably the people who are most sick, and that could mess with our results. All right, so ideally, we want random large samples. And when we do a study, of course, we want a treatment and a control or placebo. Now, computers are very good at helping us generate random numbers and random samples, and we'll be taking advantage of that as we get to machine learning. Little more vocabulary, a probability sample. So a probability sample exists before we draw any samples. We can calculate the chance that any given unit will appear in it. This is intro to statistics. We're rolling dice, we're picking random numbers, we're playing the lottery, all that good stuff. A simple random sample where we just literally just pick at random. The chance of picking any one thing out of a bucket of things is 1 out of n. So if there are 365 balls in this is an example of the Vietnam draft lottery where birthdays were pulled, and if your birthday was on that day and you were between a certain set of ages and you were a man in the United States, you were drafted into the Vietnam War. Okay, so what are the odds of pulling September 3rd? 1 out of 365. This is the basic. We've all seen these sorts of things, right? If I randomly pick a card from a pack, what's the chance that it is the king of clubs? 1 over 52. So sampling with and without replacement. If I pick a given date ball from a draft lottery, the probability that I pick September 3rd is 1 over 365. Shout out to folks from a leap year. How did they? Okay, set that aside. I imagine they just added it. Woo, tough to think about. Okay. So once I've pulled September 3rd, I have 2 options. I could replace it, which means put it back, which means that I could, in principle, pull September 3rd again. And I guess those people have to serve in Vietnam and whatever war is next. It sucks to be September 3rd. All right. So that's sampling with replacement. This is going to matter for us, I promise. Or we might not replace it, which is more likely in this particular case. So now that I've pulled September 3rd, I say, okay, September 3rd is called. I set it aside. Now the chance of pulling any particular birthday from this, what is it, an urn, a spinning thing, that thing, is 1 out of 364. This is called sampling without replacement. All right. We're really breezing along here. I really want to make sure that we're zooming in on what I think are kind of the key pieces to know here. So the law of large numbers, or LLN, tells us something very important that allows us to do all of our research with samples and say things about populations. So it's what connects the samples to the populations. The law of large numbers says that if we repeat an experiment many, 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 many times, the proportion of times we see a given outcome empirically will converge to the theoretical value we would expect. So here we have a chart of just coin flips, heads or tails. The probability of getting heads is 1/2. And we see that overall, with any number of coin flips, we get to 1/2 over time. Early on, if I flip a coin 10 times, I'm not necessarily going to get heads 5 times and tails 5 times. I might get 6 and 4 or 7 and 3 or even 9 and 1, something like that. But as I do 100 coin flips or 1,000 coin flips or 100,000 coin flips, it will converge to that expected value. All right. So you might see this called the law of averages. It's basically the reason statistics works. I'm going to put it one more way because it's worth saying this over and over again. So this is an example of rolling dice. The mean, if you roll a six-sided dice, the mean over time of all your rolls is going to be 3.5. But if I just do a couple of rolls, my mean is not likely to be 3.5. It's probably going to be something different. But as we can see, as the number of trials, the number of rolls of the dice increases, we converge to the expected value. Okay, so set it all one more time. The average of the empirical results, so what we actually see in our data, obtained from a large number of independent trials or experiments, should be close to the theoretical or expected value and will tend to become closer as more trials are performed. So a couple other pieces of vocabulary in here are the empirical results versus the expected or theoretical results. The expected or theoretical results are what we know mathematically the results will ultimately be. We know the true result in some cases for the population. The empirical results are the results of the 10 trials we just did. When we're working with data, we often just have the empirical results and we don't know the theoretical results, but the law of large numbers helps us have some confidence that what we're seeing in our sample can map to the population. But boy, we need that sample to be large and we need it to be random. How large? I'm so glad you asked. We'll talk about it more in future videos. The punchline is reasonably large, but after a certain point, there's diminishing values to increasing the sample size. Way more on that to come. All right. When we do statistics and when we work with data, we're often going to be testing hypotheses, and we're going to be doing so with models. So lightning round vocabulary coming in again. So we might want to know things with our data, such as, is global warming responsible for forest fires? Did austerity cause Brexit? Does breastfeeding increase IQ? Are violent video games causing mass shootings? Does infected water lead to cholera? All things that we either are studying, have studied, might want to study, and so on. To answer those questions with data, we need to form models. A lot of times we skip this when we think about, oh, we just have data and now we have insights, data and discoveries. Deciding what data to look at is the art of modeling. So, a model means that we can take at least some of these questions and study them systematically. But we're going to need a model for what's called the data generating process. So, what I think is going on in the world that's generating the patterns that I see. Data generating process is an A plus cocktail party word. Feel free to drop that as you go. So, the data generating process, the thing that's giving rise to the data that we see. So, a model is a set of assumptions about the chance processes that gave us the data we actually saw. All right. It's a simplified version of reality that helps us link the hypothesis with the study, research, experiment that we do. All models are wrong. They are simplified, but we hope that they are useful. So, all models are wrong is key to all of this. And many, many times in the world, when I talk about data science and data science results with very smart leaders of companies and important people all over the place, I say, well, we need to make sure that the model and our predictions are accurate. We probably need to remember that probably the results are wrong. And then people say, oh my God, how could data science be wrong? This is one way how. A model is always wrong. We are necessarily simplifying from the world. So we're saying, there's all this stuff going on in the world, but we're simplifying the causal process into just a few key pieces. So, for example, if we're trying to understand how diseases spread, we might write a very simple model where we say someone is susceptible, then they get infected, then they recover, and then they either become more susceptible or maybe they're not susceptible. And then we think about how the vaccine would fit in, and we draw these little diagrams. We're basically just drawing pictures at this stage of how all the pieces in our model fit together, how all the components fit together. And this tells us what data we're going to need later on. A little more vocabulary. The null hypothesis. When we test our hypotheses, we need one hypothesis and a null hypothesis. So the null hypothesis is the skeptical or boring assumption. There's no relationship between the things I care about. What I saw was random chance. It's the hypothesis if we're generating simulated data under which we would do that. So, for example, we might say something like there's no relationship between smoking and lung cancer. There's no relationship between drinking coffee and feeling jittery. If, as we look at our research, we say, wow, we don't see much of a relationship, we cannot reject the null. We fail to reject the null. This language is very, very specific. This is where statistics is its own language, and these words really matter. My students always get irritated because I'm very fussy about how we say these things, but it's because they mean something very, very specific in statistics. Plus, other statisticians and data scientists will roll their eyes at you if you say it wrong. So we fail to reject the null if indeed in our data we see no relationship between smoking and lung cancer in our sample, or no relationship between coffee and feeling jittery. So we fail to reject the null. We cannot reject the null. The alternative hypothesis is the hypothesis that's interesting. So if I'm doing a research study with some data, I am going to form an alternative hypothesis. You'll see it written as H1 or HA. This means that I think something other than chance made the actual data differ from the predictions under the null. It's our hypothesis. It's the interesting hypothesis. Not always, but it's the one where something's going on. It's the interesting version of the world, right? My alternative hypothesis might be there is a relationship between smoking and lung cancer, or more specifically, it could not plausibly be the result of random chance. So I reject the null. I do not accept the alternative hypothesis. I reject the null. And this gets back to the idea that we cannot prove theory. So I reject the null, or I fail to reject the null. That's how any of our research studies, any of our statistical analyses in this course are going to end. Well, then we'll discuss, limitations of the study and inferences and so on, but that's the final point, right? We either reject the null, meaning we think the world is consistent with the alternative hypothesis. We think we're in the interesting world, the world where there is a relationship between our variables, or we fail to reject the null. We don't accept the null. We fail to reject the null, meaning we think the world is consistent with the null model, meaning we're in the boring part of the world, the no relationship side of the world. It's clunky language. It's so important to get this right. So there's no other option. There's no neither. There's no both. A good theory lends itself to hypotheses that are mutually exclusive. There's one, we either reject the null or we fail to reject the null. This is the last piece for today. And this graph is something that Professor Sperling used to tell students to look at, burn into their brains, and integrate as part of their personalities. This chart is extremely important. You will see it time and again. We will come back to it in this course. There are 4 options in any study that we do. In the first row here, the left side of this table, we have the options of what we do. We as researchers might fail to reject the null, or we reject the null. So fail to reject the null, we think the world is the boring no relationship one. Reject the null, we have evidence to suggest that there is a relationship. But there's also reality. We could be wrong. At the top row, the null could be true in real life. There's no relationship between these things. Or in real life, the null is false. There is a relationship between those things. If we get it right, if we fail to reject the null as researchers and in the world out there, hey, thumbs up. Why is this happening? Okay. We fail to reject the null in our sample, in our research, and in real life, the null is true, then great, we did it right. If we reject the null and the null is false, we also got it right. That's the lower right corner. But if we reject the null, so we say, okay, in our study, it looks like there is a relationship, but in real life, the null is true, there's no relationship, we have committed a type 1 error. A type 1 error. If we fail to reject the null, in our study, it seems like there's no relationship, but in reality, the null is false. There is actually a relationship out there in the world. We've committed a type 2 error. To quote my statistics professor, one of my statistics professors in my PhD program, Robert Francis, he always told a great joke where he said, there's a type 1 error and a type 2 error and a type 3 error, which is mixing up type 1 and type 2. I bombed that joke. But the type 3 error is no one can keep track of it. It's very difficult to remember which is which. I constantly am like, wait a minute, which is one? Generally, we're going to focus on type 1 errors more in this course, but both really matter. You may have heard them talked about as false positives or false negatives. That's not exactly always a perfect mapping, but it generally is, and I find it useful, and I think it's helpful for students, so I'll include it here. So a false positive. So a false positive is we falsely say, hey, you have a disease when you don't have a disease. False negative, you don't have a disease when you have a disease. So if it's helpful to pair type 1 error and type 2 error to those just to burn it in your brain, do so. Even though it's not always going to be a perfect mapping. Another way to think about this, and this comes from Professor Sarah Sugars, who taught me this while they were teaching this section of the course some semesters ago, is another way to remember all of this is false positive is a type 1 error, because if you look at the letter P for positive, it has one line. P has one vertical line. Whereas false negative, if we look at it, that's a type 2 error, because if we look at N has 2 vertical lines. This is a sneaky little trick, but I use it all of the time. Having co-instructors is amazing for many reasons. One awesome one is learning cool stuff like this from them. So thank you for that. And that is what I have for you today. We'll see you next time.